Hello students, welcome back. Let us resume our discussion in section 3. Previously, we went through the determinant condition. When do we have inverse matrix? The determinant should be invertible. For rational numbers, for real numbers, and for complex numbers, any non-zero number had multiplicative inverse, 1 over that, the reciprocal. But we are doing number theory, and we are dealing with congruence mod m. So the multiplicative inverse condition looks like this. This determinant and the modulus m must be relatively prime. In that case, determinant is invertible. We can consider the multiplicative inverse of that, and then times this matrix, which we call the adjoint matrix. For higher system, the inverse condition is similar, as a matter of fact. Adjoint matrix is heck of a lot more complicated, but it requires nothing more than a bunch of addition, subtraction, multiplication, and some switching of order. And the determinant, well, this computation comes with the multiplicative inverse, so we need this modular inverse condition. Determinant and m must be relatively prime. In that case, invertible, so we can invert over. How to calculate the inverse matrix under this mod m is something we can discuss, and we have an example problem here. We have two example problems here, this one and that one, and we can consider higher dimension as well, but hey, what's the point? These are complicated enough. But let's have a brief review in 2x2 case first, and we can simply use the formula for determinant. Crisscross, 3 times 5 minus 2 times 4 is 7. And then 7 should be invertible modulo 12 because 7 and 12 are relatively prime. And we had the same part over here for the previous problems here. So determinant is 7. 7 and 13 are relatively prime, so we can divide by 7, no problem. 7 and 14 are not relatively prime, so we cannot divide by 7, so we had a problem here. And in this case, no problem. 7 inverse is 7 itself, so we have a unique solution like that. Okay, what if we have something more complicated? 3 by 3. In that case, the determinant condition is, the inverse matrix condition is going to be so complicated that I cannot even follow. So let me tell you an alternative method. Elementary row operation. So begin with the original matrix to the left and then identity matrix to the right. So what we're going to have is something like A and then I. And then we are conducting some elementary row operations. So switching one row with another row, switching the order basically, and then multiply a certain number to entire row, and then adding that to the other row, those kind of computation. And all those kind of computation, each of those, no matter how many we do, is basically a matrix multiplication, elementary row operation matrix multiplication. So that computation E1 is done, and then another is done, E2 is done, and then and so on and so forth, and then we do that many, many times. And then let's say we do that n times. And then, what if this entire thing turns out to be I? Then that means this part here, which I just highlighted in purple, is the inverse matrix of A. And to the right, I started from I and did exactly the same thing. So we have I, which is identity matrix, so we just have the purple matrix, the same matrix, and that's the inverse matrix. So what we see in the right-hand side is the inverse matrix you're looking for. And when you do all those elementary row operation, we're going to do each of those modulo 9 so that we can accommodate the small m business as well. So okay, all right. First, what do you do? I'm going to switch the order. So second row and the first row, switch them so that we get 1 on top left-hand side quarter. So switch these two. So I switch these two as well. So just switching the first row and the second row. Next, I'd like to remove these 3 and 4. So multiply 3 to the first row and subtract it from the second row. Multiply 4 to the first row and subtract it from the third row so that we get 3 and 4 removed. So multiply 3 to -2, so -6, and subtract it from 1, so we get 7. Multiply 4 to this -2, so you get -8, and subtract from 3, so that we get 11, etc., etc., and we do the same thing. And then some simplification is in order, I guess. We have big numbers. So -9 is congruent to 0, mod 9, and -17 is congruent to 1, mod 9, and 7 is congruent to -2, again mod 9. And then likewise here, a bit of simplification here as well on the right hand side. I don't know whether those are necessary though. Anyway, we got this. And then let's remove these, -2 and -2. So add third row to the second row. So 2 plus -2, so that becomes 0. 1 plus 0, so 1. Add third row to the first row. 2 plus -2, so we get 0. And 1 plus 4, so we got 5. And we do the same thing to the right-hand side, adding the third row to the first row, adding the third row to the second row. All right, and we have 2 here and 0 there, so we switch the order of second and third row. Now we have 2 here. What I want is 1. So I have to divide by 2. How do I divide? Modulo 9. I have to multiply the multiplicative inverse of 2, and that's 5. 2 times 5 is 10, and that's congruent to 1 mod 9. So multiplying 5 to the second row. Multiplying 5 to the second row. Multiply 5. 2 times 5 is 10, so we have 1. 1 times 5 is 5, all right? And then multiplying with 5 to the right-hand side, do the same thing. 5 times 5 is 25, and that's congruent to 7, etc., etc. Finally, we have to remove these 5s. Multiply 5 to the third row and subtract from the second row. Multiply 5 to the third row and then subtract from the first row. That's how we get these two removed out. And then we do the same thing to the right-hand side, and we get this expression. And then again, some simplification is in order. So simplification, mod 9, we end up with the final result. That is the inverse matrix, modulo 9. This kind of process does not involve, it does involve division here, right here. 2, this one here, this one here, becoming 1. We have a division here. We divide it by 2. So is that the only division? Is that the only division? Let's see. Is this a coefficient matrix? 3, 1, 3, 1, -2, 4, 4, 3, -1. Okay, all right. Determinant is 20, and that's 2 modulo 9. So that's determinant is 20. And we're doing mod 9. Oops. So 2. So we have to divide by 2 at some point, and I just divide it by 2 right here by multiplying by 5, which is multiplicative inverse of 2. So you can see that, you can see the division, you can see the division by the determinant, but I don't want to go too deeply into linear algebra. I'm already really deeply in. Anyway, this kind of elementary row operation business can be programmed appropriately and made completely algorithmically. And for that, it could be a major pain in the rear end for humans, but for computers, it's a piece of cake. It's just a matter of writing a program, and good programs are already written. As a matter of fact, more than 50 years ago, I guess. Maybe close to 100 years ago. Anyway, we have the inverse matrix. So apply the inverse matrix, and we get the unique solution. So we can handle a little bit higher matrices as well. And what if you have 4x4 or 100 by 100 and things like those? In that case, well, exactly the same technique, the elementary row operations apply, just longer, elementary but tedious, and that kind of thing is perfect for computers. And how to write those programs is, of course, a bigger issue, but as far as mathematics is concerned, we cover them all. We still have one more topic to go, when the inverse does not exist, how to handle those kind of things, but that's gonna be another topic. So let's meet again in another optional video. For now, that's it.